And perfect. So thanks a lot for the invitation, giving me the possibility to speak here. So what I'll talk about here is results that we have together with Yunqiao Liu, Srinivasana Runchalam, and myself. I'll give some motivation. Most of the talk will actually be mostly motivation for that result. And so we are trying to do in that paper is essentially in a very restrictive model that we're setting sort of in the machine learning setting. We want to be able to sort of formally prove some sort of separation. So there's like a toolkit that we have in quantum machine learning, which I'll introduce. And we want to show that using that toolkit, you could do something in principle you can't do classically in terms of a learning problem. Okay, that's what most of this, what this result is. Obviously, making such a strong claim comes with a lot of caveats. And the caveats being that the problem that we show the separation for is completely artificial and very much constructed. I don't think anyone would particularly care about learning that particular problem for which we have shown that separation, but going further, there's actually ideas you learn from this, and you can maybe look for places where you could find artifacts like that as well. But before I basically go into that result, let me give you a bit of a background from where I'm coming from, where a lot of people are coming from when we think about these algorithms. And so we're sort of motivated by sort of what people call it near term, some people call it NIST devices and so forth. And that's the following setting. So you have a, say, reasonable number of qubits, not too small, not too big, that an experimentalist can actually build. You don't have error correction. So that's a big caveat, because most of the algorithms we know that have a provable speed up or have an advantage over classical algorithms are algorithms that will definitely require a fault-tolerant or error-correcting architecture. So what is that kind of architecture we're saying, okay, we're playing around with right now? It's essentially the following setting. So you have that device, it's going to be noisy due to its coupling to the environment, and that will limit the device's usefulness. So what you can see is basically the device coupled to environment, things start to decohere, and essentially all the quantumness goes away and becomes a classical mixture. So a naive approach, what you can say is, okay, all algorithms I'm trying to do is I'm going to restrict myself to circuits that are in some sense short relative measured to the other algorithms that are out there for which there are known separations, but sort of at the length scale or time scale of the coherence time of your device, right? And so what you could do then in that setting is basically, okay, we do something, all our algorithms are going to be very simple. There's just going to be some unitary circuit that you apply. In the end, you measure something, you draw statistics, you sample stuff and compute some observable. Because if you do that, there are tricks actually that allow you to get some reasonable observables within that time window that you can draw value from. And so that the tricks that we've been thinking about, many other people have been thinking about, these quantum error mitigation techniques. But I will not be talking about that. I want to talk about the machine learning stuff. And before I dive into that result, let me give you some background of what motivated that. So we're motivated by the thought of thinking about feature spaces in the context of quantum mechanics. And so about 2 years ago, there's been 2 papers that came out, 2 to 3 years ago, 2 papers that came out, both which basically made the observation that, oh yeah, there's some very convenient confluence. People in feature spaces, they want Hilbert spaces, and nature provides them in context of quantum mechanics. Maybe there's something interesting you could do there. And at that point, basically, those papers came out, and we thought about, okay, there's some ways of basically, could you use that Hilbert space that physics provides, essentially do something interesting that you couldn't do otherwise. There's some different takes in both papers, but both had the rough idea, okay, there's a Hilbert space, why not use it? Let me give you some background from our motivation of how we approach that. So let's say we take the simplest problem we can wrap our head around in our context. So let's just do some really simple supervised learning problem, and let's try to construct a classifier, right? So that's your conventional task. And what people often suggest in the quantum literature are so-called quantum neural networks. Okay, so how do these neural networks look? Just a brief recap is basically, oh, there's some initial step where you basically input a datum that you basically map somehow into the quantum computer by preparing some initial state. And then your goal is to basically apply a shallow or reasonably sized variational circuit with tunable parameters that you can optimize, because it looks kind of like a neural network. And then in the end, what you could do is you could go and measure in some local basis or do some measurement and compute an observable based on this measurement. And then basically, once you have that observable, what you can do is you can assign a label based on thresholding of that observable, right? So if that observable is larger in the plus case for the plus outcome than for the minus outcome, so it's a plus minus valued observable, you see more pluses than you see minuses, then you declare, okay, that variational classifier does this, okay, the quantum neural network. So in the simplest setting, how do you set this up? Is say, oh, you map the data by a bunch of single qubit rotations, so now you're, say for 5 qubits in the trivial case, you have like 5 real numbers, and you want to classify something that is 5 gray pixels or something, and then you basically start rotating every single qubit, say a Y rotation around that, take a tensor product of those, then apply an arbitrarily fancy and complicated variational circuit, you measure and you declare that thing. And so that is one example of how people think about in a very abstract way, think about coming up with classifiers on a quantum computer. So before I talk about this, allow me a very, very small review that I think everybody should be familiar with, but there's a good reason to just run through this. I think you're also familiar with classical support vector machines, right? So classical support machines, you have 2 clouds of data, you want to linearly separate that by some line. There's an optimal line in the sense of giving you a good upper bound of the generalization error, i.e. the line that has the largest margin, and then your classifier is essentially just an inner product with the normal of that line, thresholded, and you basically wonder, oh, am I to the left or am I to the right of the line? Okay, so for more complicated data sets, which are not as easily linearly separable, what people use are feature maps, right? So you take that datum, use a nonlinear map into potentially very high dimensional space, and hope that the data that was not initially linearly separable in that higher dimensional space does become linearly separable, and you will find a linear classifier, linear separator with a large margin around it, right? And so you could complain about the fact that, okay, sometimes these maps take you to very, very potentially even infinite dimensional spaces. How do you ever compute anything there? And there's a very common trick, which is the kernel trick, which basically tells you, well, you can look at the dual basically of the original margin maximization problem, which was a quadratic program, and you realize that everything that you would like to express in that quadratic program in terms of the dual, you can do by only knowing the inner products in those larger in that larger Hilbert space, and that inner product function is referred to as the kernel function. Okay, so the reason why I review this is the following. Those quantum neural networks that people basically look at, they're essentially at best SVMs, right? So let's look about that. So if you look at that decision rule after the way I've explained it initially, you prepare an initial state, you follow it by a variational circuit, and then you do some thresholding. So if you now go into sort of the infinite shot limit, so of course this is sort of statistical, you only get sort of a rough an estimator for that difference, but suppose you wouldn't, then that exact probability of observing some outcome y, a label y, would be just the function that we have here, right? That function depends on that expectation value. So it's an expectation value between that initial state prepared, the observable f that you want to measure, and the variational circuit. And now, if you just rewrite this a little bit, then you could say, okay, let me go and just go into the Heisenberg picture, flip the evolution onto the observable, and now that is a observable that I can rotate around. Then what you have written there is essentially, oh, it's just the sign function of an inner product between a normal, i.e. that observable, in a quantum operator space, and a feature map, which is a projector onto quantum states. And it's just an inner product between those plus the potential offset, which is exactly the linear decision function you have with an SVM. So all that these variational circuits that depend on nonlinear parameters, all that they do is they generate a linear separating hyperplane in the space to which you have mapped the data. So in that case, it's quantum state space to which you have mapped the data, right? And so there's now ways of choosing good linear separators, as we know through SVMs. All that you need to be able to do is essentially, oh, you need to only compute the kernel function, or essentially the inner product between those feature maps in these states. Okay, so what you can realize is, so what is the inner product that you want to use? In that case, it has to be the trace norm or the Hilbert-Schmidt inner product, and effectively that reduces to the 2 fidelities between those initial states that you prepared. Okay, and now what you can observe at that point is, so in the example that I gave earlier, I mentioned that, okay, you could use a bunch of product states to essentially load your data, then you know that, oh, in linear time, you can actually compute that kernel function. So the fact that you used a very complicated variational circuit after having basically prepared a tensor product initial state, you're not going to expect that you will have a classifier that does anything better than an SVM does, but where you go compute by hand the inner products between all those feature vectors, right? So is everything lost at that point? No, of course not. The interesting point here is basically, it's maybe the lesson to take away here is more interesting to actually now think about those feature vectors and the feature states and to wonder how you map them into quantum state space, as opposed to the variational circuit that follows them, because you could mimic that effectively by classical SVM using a kernel trick. Okay, so to reduce that, essentially, we made 3 observations in that paper. Number 1 is basically what I just repeated. I'm just going to repeat that is, oh, all these variational circuits, they apply some unitary circuit in the input state, and you measure an observable. So effectively, what you're doing is you're going and drawing linear separators into some form of a quantum feature space or quantum state space. That quantum state space for a single qubit, say, is just the Bloch sphere. So what you're doing is basically you're just cutting the Bloch sphere into 2 parts and put data on one side, data on the other side, and classify based on that. So the interesting thing is now, of course, so let's think about that map actually a bit more. So the next thing you basically have to say, in that picture, what is it that you have to think about in terms of the map, right? There's actually different notions. That's sort of different notions between one approach, the PRL that I mentioned earlier, and ours. What we say is we declare the map to say, well, it's kind of that picture where that comes from that quantum neural network. What you declare as a feature map is essentially just a projector or a quantum state space. So there's the density space of density matrices, and the inner product basically is being the fidelity. The other way you could do it is you could say, well, quantum mechanics comes with a Hilbert space by itself. You could use just the Hilbert spaces that sort of L2n or C2 to the n when you work on a qubit space and declare that to be the feature vector. The problem is if you then of course use the natural inner product and the classifiers that you construct that way is actually something that is going to be sensitive to global phase. So what you can see is basically a simple trick is basically if you look at the feature map you've mapped and you realize that in sort of Hilbert space, they're not phase like having phi of x and minus phi of x are physically exactly the same space. So they're just equivalent up to global phase. Whereas if you work sort of in density matrix space, having a minus sign of the corresponding Bloch vector or the evolution, which completely makes the state orthogonal. That's the next observation, which Hilbert space you want to work in. And the third observation is, okay, that I mentioned towards the end is, okay, if you now start with easily preparable states that you could do, you always have to ask yourself, okay, do these lead to any classifiers that give you some form of an advantage over classical methods? So as I mentioned, there's like product states, and you can immediately see that, okay, I can compute kernel functions for product states, i.e. the product between those individual qubit rotations in linear time. So that's probably not going to be the case. There are certain RBFs, Fourier displacement operators, or other circuits that have been proposed, IQP circuits, all of which you can compute classically just as well as you could on a quantum computer. And so the task is actually, rather than worrying about what variational circuit you apply to this, you can still do that. The task is more, what kind of feature map circuit can you use so that you end up with a kernel that is basically hard to estimate or compute classically. And the reason why I say estimate in this context is basically that a quantum computer only allows you to sort of sample, as I will see in a second, that kernel matrix up to an additive error, right? So the funny thing is now, what you can see is immediately you know, how you basically get this kernel. The way you get this kernel is basically, suppose you take this first step, this data loading step for some datum xi, you undo that data loading step with some datum xj, and you have a certain transition amplitude. And if you try to estimate this transition amplitude on a quantum computer, so I start in 0, apply ux, undo ux, but with a different x, and then count how many times I see the 0, that transition amplitude ends up being exactly the kernel. So this is something you can estimate on a quantum computer, but again, only up to an additive error. So after I've said that, it's basically, there's a question, right? You just wonder, okay, let's try to sit down and write down some hard kernel functions, and they exist. So without doubt, there's quite a few transition amplitudes which are very hard to estimate. On a classical computer, the question is now, cool, now once you have this component, and that component is difficult, and then you run your standard SVM algorithm, does that actually mean you can do something as a learning problem better than you could have done classically, right? Just having your algorithm overall having like one component which is difficult to do on a classical computer doesn't necessarily implicate that the algorithm that you're using does something better than some other algorithm could have done. It's just that maybe one step you chose to do turned out to be very difficult. And now we come to the point of our paper. This is essentially what motivated our work, right? So what we want to do here is basically, we want to formally show that there are classical learning problems that you can write down and construct with sort of all the parameters in the right place, meaning, oh, it's some data that is being generated classically. You take into account all the caveats of quantum computing, meaning, oh, you have some sampling error, it's the additive error of the kernel function that I've been talking about. We allow ourselves to have error correction here because the Featuremap circuit that we come up with or write down is actually kind of a tricky one. So that won't be itself a near-term Featuremap. But then it's basically, with all those things met, can you show that there is a way of having data that you cannot learn classically, but that this quantum machine learning algorithm based on those kernel methods can actually learn efficiently? And so that's what we're setting out in that paper to do. So what do we mean by learn here? So we sort of, in the standard PAC learning setting, we define a concept class, we sort of set up, we explain what our training samples are, we declare test accuracy, and then we declare that, okay, we can efficiently learn that concept class from M training samples and so on and so forth, if you're sort of being able to do that in the PAC learning. So with a certain probability, you should achieve a fixed test accuracy, say 99%, and the principle, yeah, with polynomial efforts. I mean, looking at polynomial minisamples and having actually an algorithm that takes polynomial time. Okay, so what is the problem that we base this on, for which we basically go and construct the learning algorithm? So we base this sort of on the discrete logarithm problem. So if you're not familiar with that problem, it's the following problem. So you're given a modular group, so integers 1 to some large prime number p, and so you have this list of 1 to p minus 1, and that group is basically just multiplication of those numbers modulo that large prime number. Okay, and so since it's a cyclic group, there's a generator, which means that you can basically visit every element of the group as the power of some generator. So if someone hands you the generator, you basically say, okay, I can visit element y by applying the generator x times mod p and cycle around, right? And so that's sort of this exponentiation map, which is pretty easy to do. And it's generally very difficult to compute the inverse, meaning I give you y, I give you the generator, and I'm asking you, so which x, how many times did I have to apply the generator to actually visit this element y in the group? And so most of the cryptography that you have, such as, I don't know, or factoring, can be reduced to this to this problem. So, and it's generally believed that this is something a classical computer cannot solve efficiently in polynomial time. Okay, right. So this is basically the actual problem we base our learning algorithm on. And so what we do now is actually pretty simple. So suppose you take this group that I mentioned, you basically cut it into two pieces by drawing some random element from the group, and say basically everything larger equals modulo this number s. Basically, we're going to declare +1, and everything less than that we can declare -1. But we do that sort of in log space, so in the space of x's. And then what we do is we raise this stuff to the power, use that as the exponent of g, and basically hand whoever wants to learn that data set essentially. So you now have a bunch of samples that essentially look very, very much random to you, and they're labeled. And now you could ask, okay, now try to classify whether this is +1 or -1. Okay, so that means you have like you assume here that p is a large number, right? And p is sort of 2 to the n, where n is maybe your number of qubits that you would carry around. And that way you say, okay, you have 2 to the n different concepts classes that you try to learn. Now you label one element in there, and now you're asking, so okay, let's construct a classifier for that. So the interesting thing is only being able to predict the label, which on the face of it looks like an easier problem than the original problem of solving the discrete logarithm problem, can be shown to be just as hard as the discrete logarithm problem, right? Meaning, if you could only learn that one bit from that one classifier, so you could construct any classifier that based on seeing, I don't know, a reasonable polynomial number of samples in the precision by which you want to predict the correct label, if you could only have one that does so with slightly above 50% accuracy, right? That classifier would actually be enough to solve the original problem that we assumed to be hard in a classical computer. So by that, you can essentially conclude, okay, yeah, there probably isn't a classical classifier that is able to do that, independent of the form. On the other hand, as soon as you can solve discrete logarithm, it's actually not a difficult problem to solve, right? So, but what's the basic idea? So we piggyback on a result by Bloom-McCauley from 1984, which basically allows you to basically learn the discrete logarithm bit by bit by bit by taking the square root and doing then some amplification of your some boosting of the correctness of predicting that bit based on the classifier from seeing many samples. So based on that, you can basically say, well, once you have 1/2 plus poly n, you can learn one bit, and then you can basically do that square trick and go on and produce the full discrete logarithm problem, basically by going backwards and learning bit by bit of the exponent that you would like to know. Okay, so just being able to classify is enough as that. So just the other thing is there's actually a quantum algorithm that does that too, without actually having to go through those notions of using the kernel method. Because as I said earlier, as soon as you know a way of actually doing the discrete logarithm problem, you can actually classify that data correctly. And one way to do this, one quantum algorithm, was essentially that, okay, just look at the data, just factor it, go back into the log space, and then just cluster or do something else. Because then the learning problem essentially becomes easy in the quantum computer because you can do it because of Shor's algorithm, right? So, but again, that's not the point of what we're actually trying to do here. We're not interested per se in that learning problem. We're not interested in the fact that, okay, there is something that a quantum computer can do that a classical computer can't. What we want to show is whether this approach, basically, by just having kernel functions that are difficult to estimate classically, does that lead to something that you couldn't have done classically? So we piggyback on that result, essentially. Okay, and so the interesting part about that is essentially what was driving is basically every step that we're doing is that every step, basically, when you ask, so what is it that you would actually ask for a learning problem that that you could do efficiently, computer couldn't do classically, it essentially ticks all the boxes except for the presumably most important one, and that being, oh, it's actually a relevant problem that you would care about, right? So how do you do this, and what is the feature map you choose? Well, what you do is basically the feature map that you use is essentially the following state. You take some datum x, which is some bit string, by which you represent that integer from the modular group, and then you prepare the superposition state. So you basically take that x string, and then you basically say, okay, x acts on all the elements gi, where I should be running 0, I equals 0 to 2 to the k. And the funny thing is that that number, essentially, that state can be prepared in polynomial time on a quantum computer. Okay, so why is that helpful? So these states, they act sort of as interval states. And if you now look at that old picture, they're sort of supported in log space, sort of on a neat interval around the x function for which you want to assign the label. And if you look at this sort of this interval picture, then okay, there is actually state that you could write in quantum feature space as a projector that would separate you to the left or to the right of this. All of these things are garbled, but up in feature space, it kind of looks neat and separable. And what happens is basically you actually are able to show that, okay, depending on if you use like k bits for your interval states and so forth, you can essentially get a polynomially sized gap, or a margin in which majority of like a large fraction of the states that's out. So based on that, you can essentially start showing a learning result. So what we do is then we show them, okay, that your conventional L2 soft margin SVM is actually using that feature map, using those properties, is actually to learn that thing. So the actual algorithm that we run in theory is essentially the dual of that. The reason why we work with the L2 soft margin is because it's sort of nicer to show that there's parameters for which you can essentially always choose the dual to be convex, because in principle you could have like sampling errors in the you do have sampling errors in K, so this is this additive error, but you can still show that, oh, that's still a convex program. You can always have the parameters behave right. And then what you can do is basically the only thing that you have to essentially do in the end on a quantum computer is then to actually go and estimate this kernel entry onto an additive error, while most of the other stuff is essentially done on a classical computer. Okay, with that said, what you can then prove is essentially that you can efficiently learn that labeling function to arbitrary precision in terms of polynomial resources. Okay, so what is actually another interesting component of this proof? There's the following part of it, where we say, well, it has a rigorous and robust, and the robustness part essentially refers to the following, that as I mentioned, you have these additive sampling errors. And so now if you're working in a setting where now every entry in the kernel is essentially perturbed by some statistical sampling error, can you still show that your classifier does what it's supposed to be doing? And can you actually essentially also come up with a bound on the generalization error where the classification function basically on a shot-by-shot basis produces some form of error? Okay, and so that is essentially shown in that paper, and you can see basically that your upper bound basically scales as 1 over m delta squared plus delta. So where m is the number of training samples that you can see, delta is the function that I introduced earlier, which you can make decay polynomially. And so you basically get an upper bound that decays polynomially on your generalization error. And I think with that, I'm more or less done. And I'd be happy if there's any questions. Hello?
Okay, so Chris, are you open the floor for questions?
Yeah, should I do this? Sorry.
Yeah. Yes. I think we have some time, right, for questions.
Yeah, of course, exactly. Yes. Sure.
Yeah, so maybe I can start. Thank you for giving this very insightful talk. So I just want to understand my understanding is correct. Like so the kernels, right? We are trying to learn. So those kernels, functions are approximated by the quantum gates or quantum circuits. Is that the idea?
Correct. No. So the kernels are exactly. So let me share that. Show they're essentially transition amplitudes that you estimate. 1 second. If you look at this, so suppose you have some circuit that prepares U of xi that prepares the datum. So in this case, that in this example, you go and you prepare this state essentially, the projector into the state. There's a polynomial circuit called U of x that prepares that state. And for you to estimate the kernel, what you have to do is essentially you have to run the forward evolution of that circuit ux, and then you go and you run the backward evolution with another datum, say y uxj. So, and then what you do is you start in the 0 state of your quantum computer, evolve forwards, evolve backwards with a different datum, and then you count how many times you basically see the 0 string again. That's a way of how you estimate that kernel function on a quantum computer effectively. Right? So in the case where xi and xj, where they end up being the same datum, you basically haven't done anything. So your diagonal of the kernel is always 1. So you evolve forward and evolve backwards. But sort of if they start differing a bit, that transition amplitude essentially dies down. The funny thing is that a lot of the conventional kernels that people use, such as the polynomial kernel, radial basis function kernel, some of those Fourier, Anon, ANOVA kernels and so forth, they can all be expressed that way, as essentially a transition amplitude. The question in a larger scheme of things is essentially, okay, can you come up with more interesting circuits that give rise to such quantum kernels that you can't estimate classically, and for which you have some advantage in terms of learning?
So those quantum kernels, do they involve any learning, or like when you specify what kernel function you want, that state has already been designed?
Right. So in this case, in this particular example, we a priori fix the feature map, and learning happens all classically. Right. So it's just your conventional SVM. What you can do though is basically in many cases you don't. That's a result that I haven't presented here, but what you can do is essentially in many cases you don't really know how good that or what a good kernel function would be. You could essentially use parameterized circuits as components within the feature map. So you basically now have a circuit family that depends, say, on some parameter lambda that you can optimize, and the datum xi that you can do that you can optimize, where you can actually select among a set of circuits a good one that gives rise to a good classification error.
Right.
There's another paper where we do that. Right.
Thank you. Any question from the audience?
Yeah, I have a question.
Sure.
For the variation quantum circuit U, is there any heuristic to design such circuits?
For say U lambda of x, yes. So we have one result that we refer to as sort of learning, like having kernels for group structure, and so the heuristic that we came from essentially is motivated by the quantum feature state for which we can prove a formal separation. All right. So that state, if you, I don't know, you can all see the screen that I'm sharing. Is that correct? Yeah. Okay. So what you can view this state as is actually kind of a funny thing. Is you can say, okay, there is actually some universal and good reference state, which is sort of this universal sum over the GI. And what you effectively do is what your feature map circuit does is essentially it acts with a unitary representation on that reference state. So what you do is you have like that unitary representation depending on x, and that acts on that reference state. So in this example, I haven't written it out. It's essentially the unitary representation is sort of the regular representation that would act on some reference state, call it psi, where psi is the sum over e equals 0 to 2 to the k, where x is 0, right? And so what you can see is there's a crass difference between what you use as the reference state for these things, right? So if you were to go and use as the reference state this uniform sum, we can show that you have efficient learnability for that learning problem. However, if you now go and take sort of just 0 as the reference state, or just the identity element of corresponding to that group as the reference state, then the kernel you end up with is pretty much just the identity kernel, which is arbitrarily bad. So the difference is basically, what is it that you choose as your fiducial state is then your degree of freedom that you want to optimize in your learning problem. So that's it's called covariant kernels for data with group structure. That's the paper in which we do that.
Thank you.
Right. Thanks.
Any other questions from the audience? So Kristen, maybe can you share some tips like for machine learning researchers who are interested in delving into the quantum machine learning field? What topics or what I don't know, literature, what direction they should have?
Kernels, of course, absolutely kernels. Everything kernels. I'm kidding. That is one thing. Yes, I actually believe that that's something interesting. Yeah, that for now, I mean, there are many. Yeah, that's one thing. Then what I would be interested in personally as well are again sampling-based algorithms. So you could use those shallow depth circuits to generate probability distributions and see where that fits and so forth. Those are the kind of things. So I mean, what is probably most needed from the kernel perspective right now, I would argue, are basically good applications, right? So now you have this setting where you say, okay, you can in some fringe case prove a formal separation and so forth. Is there any place where this is actually useful? So this is something that I'm personally very interested in.
Thank you. Yeah, thank you for giving a nice talk. So last chance for asking questions. Oh yeah, as a question. So is there any real world data where quantum kernel method outperforms classical kernel method?
So what is define real world data? Meaning, let's go to some MNIST data set and see how that does there. I don't know, to be honest. If you mean that, are there some other ones? I don't have an example for that question, essentially, where you say, okay, all right. So the question that, because it's sort of it's a two-pronged thing, right? So what do you mean by outperform? You mean you could run some numerics and then basically see, okay, maybe this does better than some other classifier or the bunch of classifiers tried. The weird thing about quantum algorithms is essentially that you have a pretty high bar to meet in some cases, right? Because I mean, there's a lot of overhead that goes into building a device, running things on the device, and so forth. And so what you want to make sure is that you do something that's actually sort of non-trivial, right? So if you mean, outperform, in practice it does. I have to admit, I mean, there's probably many things you could try and see what does better. And so in some construed setting, yes, sure, this does better than radial basis functions, this does better than that, sort of, but universally outperform, I don't think that's known. And it may be a bit too much to ask for, that you basically have some formal reason of why your quantum classifier does much better on this problem than the classical one, if in practice it just happens to be that case. I mean, the thing is there, what hinders that, or why you couldn't make such claims right now, is the fact that experiments and devices and size and so forth are only gradually getting to the point where you could try these things and see whether you're sort of better or competitive in some real world problem, right?
Yeah, I think it's a great point. And yeah, and thank you, Kristen. I think we are on top of the hour, and thank you again for giving the talk.
Cool. Thanks a lot. Thanks a lot.
Kristen. Yeah. Okay.